So again, in Lab 7, we're going to start out with some simulations. So you go into the Physics 1100 folder, and you want to go into the Lab 7 folder. And there's 3 collisions in here, and we're going to look at all 3 of them. So double-click to open up the first one. And in your report, you're actually going to sketch these before and after the collision that we're going to run in this simulation. The first one's actually started for you, but you'll draw in the rest of them. Another thing you need to do is you'll need to write down some stuff right now. So you want to write down the mass and the velocity of the first ball before the collision, and the mass and the velocity of the second ball before the collision. And then you're going to calculate the momentum of the first ball before the collision and the momentum of the second ball before the collision. Then you'll run the simulation by clicking the Run button, and after they've collided, you can stop it too. And then here again, you'll want to sketch this into your report, and you want to write down the mass and the velocity of the first ball after the collision and the mass and the velocity of the second ball after the collision. So once you've got all your data and have calculated your values, then you can move on to the second simulation. So I'll close this down and open the second collision. And in this one, you'll notice that the balls are headed towards each other. So one of them has a velocity pointed in the positive direction and the other has a velocity pointed in the negative direction. Again, write down the mass and the velocity of the first ball before the collision, the mass and the velocity of the second ball before the collision. And here's one thing to pay attention to. Remember that velocity is a vector. It's got a direction. That means that momentum is also a vector. You need to keep track of minus signs. So when the velocity is pointed in the negative direction, write it down with a negative sign. If you don't keep track of the minus signs, you won't be able to show conservation of momentum later. So you grab the data that you need before the collision, draw your sketch, and then you'll run the simulation and stop it after the collision. And again, write down the mass and the velocity of the first ball after the collision, the mass and velocity of the second ball after the collision, keeping track of the minus sign on the velocity that's negative, and then you'll calculate the momentum of the first ball after the collision and the second ball after the collision, and make your sketch. Then you can move on to the third simulation. So again, close this. If it asks you to save changes, say no like usual, and open up the third collision. And in this one again, they're pointed towards each other, so make sure you keep track of the minus sign on the velocity that's negative. Write down the mass and velocity of the first ball before the collision, mass and velocity of the second ball before the collision, run the simulation, and in this case they just stop, so they stick together and don't go off anywhere afterwards. Again, write down the mass and velocity of the first ball after the collision and the mass and velocity of the second ball after the collision. Then calculate their momentums. And then you're done with this third simulation. Now before I show you the equipment for Lab 7, I do want to point out something that's true in the lab manual for Lab 7, and that is that when they tell you to summarize your results in a well-titled table, for the first time ever, they don't give you the table. You're expected to draw it in yourself. Likewise, for the conclusion, it doesn't give you that bullet list of things that should go into your conclusion anymore. You're expected to know how to write a conclusion by now and to do it on your own going forward. So this is going to be true for the rest of the semesters, that you'll be writing your own conclusions and creating your own tables without any extra help. It's important you know this now because this is also going to be true for the lab exam, which is your next lab, is you'll have to write your own conclusion without a bullet list. Now you are allowed to have a formula sheet in the lab exam, so if you wanted to put the bullet list on that, you could, but just be aware it won't be there by default. I have put an information video up about the lab exam and what you should do to prepare for it, so I recommend you watch that a little bit early so that if you've got any questions, you can find your lab instructor and ask them. So now we're going to talk about how you do the experiment. So first of all, you're going to need to weigh your 2 carts. So cart 1 is the one that's closer to the sensor. So you'll weigh cart 1, and then separately you'll weigh cart 2, and then you want to weigh them together. So just stack them one on top of the other and weigh them as one big chunk like that. The reason why is that when we weigh them together, then we know what the uncertainty is and we don't need to do a calculation of it. And second, I know I'm always telling you guys to do this, but be very careful to level your track well with this experiment, because this is another one where if your track's not leveled well, you'll have a really hard time getting good agreement between your numbers. So do that as carefully as possible. It does make a difference with this experiment. Now we're going to study an inelastic collision. So these 2 cars have Velcro pads and they actually stick together. So that means that if I run one of them into the other, they'll stick together and just continue on together as one. So an elastic collision is a bouncy collision. They bounce apart. An inelastic collision is a sticky collision. They stick together like these do. Now, theoretically, in an elastic collision, a bouncy one, we expect both momentum and kinetic energy to be conserved. This is an inelastic collision. Theoretically, we expect momentum to still be conserved, but for kinetic energy not to be conserved. And you can kind of understand why. If you think about, say, two balls of putty, you throw them together, they go splut, and they stick. Some of the energy got lost due to deformation of the putty. It changed shape. So to a very minor extent, the same thing's happening here with the Velcro hooks. They flex, and we lose a little bit of energy to that. We also lose some energy to the sound they make, but that can happen in an elastic collision also. So theoretically, in this collision that we're studying, we expect momentum to be conserved, but kinetic energy not to be conserved. So the way in which we take data with this is we're going to take one of these cars, put it about 2/3 of the way down the track, start the other one at about the 15 centimeter mark, so edge of the dead zone, and we're going to send cart 1 down the track. It'll collide with cart 2 and they'll roll off together. So cart 2 initially is stationary. After the collision, they roll off as one. The quantities that you're going to need to be calculating are momentum and kinetic energy for both of the carts, both before and after the collision. So because you have the masses already, what you actually need to get now are the velocities before and after the collision. So I'm going to show you on screen how you get the velocities using the velocity program. So in a lot of experiments, we've been using the acceleration program, but in this experiment, it's better to use the velocity program. It's got a larger graph. And just to remind you, here's how you set up your equipment. One of the carts will be at the edge of the dead zone, the other will be about 2/3 of the way down the track, and their Velcro bumpers are set up to stick together. So I'll click the start button, and then send one into the other. They collide and carry on down the track together. And you end up with a graph like this. Now this stuff over here, this is just the bounce back at the end of the track. We should ignore this part entirely. Over here is where things are interesting. So this kink in the data that you see is the point where the velocity changed, and it changed because that's where the collision happened. So this was one cart moving at a constant velocity before the collision, and this is both carts together moving off down the track at a slower velocity. Now we need the velocities before and after the collision. And to get the best results, you want to highlight just 3 to 4 data points right before or right after the collision. And the reason why we only select a very tiny amount of data is that way you don't have to worry about friction, changing your average velocity a little bit in a way that makes it hard to get good agreement. So to get the best results, highlight just about 3 or 4 data points right before the collision, and then put a linear fit on that to get your value. And then you'd want to print off this graph and paste it into your book. And then you also will need the velocity right after the collision. So again, just highlight about 3 or 4 data points right after the collision to get your velocity afterwards. And again, print this graph and paste it into your report. And that gives you your velocity just before the collision and just after the collision. So once you've got your masses and your velocities, then you're going on to your calculations. So you would go to the lab manual and you're going to calculate the momentum before the collision. Make sure you show all your work and include the units, and they do suggest some units that are good to use. And you'll also find the uncertainty of the momentum before the collision. Then you're going to calculate the momentum after the collision and its uncertainty. Then you'll do a percent difference between the two values, summarize your momentum results in a well-titled table, and then write a conclusion where you say whether your values are in good agreement and whether that verifies the theory. And then you carry on, because you're also going to do this all for the kinetic energy. So you'll also find the kinetic energy before the collision and its uncertainty. And then you'll calculate the kinetic energy after the collision and its uncertainty. You'll do a percent difference between them, summarize your results in a well-titled table, and finally, write a conclusion. The only thing that's tricky about this second case with the kinetic energy is, you remember, in an inelastic collision, a sticky collision, we don't expect kinetic energy to be conserved. So think carefully about what the theory predicts and what your results mean relative to the theory. Should they agree with an uncertainty or not?